Friends, I want to tell you something from the heart. What is the most dangerous thing in the world of VSD? Not motor failure, not cable problem, not EMI issue. The most dangerous thing is a wrongly tuned PID loop. A motor is a machine, but a PID loop is a brain. This brain controls the entire process, decides the behavior of the whole plant. If this brain is stable, the system will run smoothly, the plant will become reliable, production will remain safe. But if the PID loop becomes unstable, then hunting begins. Oscillation increases, pressure spikes occur, water hammer is created, tripping happens, overheating occurs, and the entire system feels like collapsing in a chain reaction. Friends, in this part 7, we will understand all those things about the PID loop that you may have never heard of in the industry. This episode is going to be a game changer because all the drives, pumps, fans, and compressors running in your plant, their stability, this PID is in your hands. Today, we will understand PID not just as a theory, but as a real world engineering science. Let's get started. Real engineering level PID loop mastery. Friends, as soon as people hear the name PID, they get scared. It seems like a very complex mathematical formula, which only software engineers or high level programmers can understand. But the reality is completely the opposite. PID is a natural thing, a behavior that we follow in our daily life without thinking. Think you are riding a bicycle. If the bicycle tilts slightly to the left, you automatically lean to the right. If the speed drops, you pedal faster. If the speed increases, you slow down the pedal. These simple reactions are the foundation of PID. Proportional means giving an immediate reaction to the system. You see an error and immediately make a correction. Integral means gradually eliminating small mistakes, small errors that you don't notice. The integral keeps fixing them over time until the process settles cleanly. Derivative means keeping sudden changes under control. Just like when a quick jerk comes to the handle of a cycle, you smoothly absorb that jolt and keep the balance stable. These three actions, proportional, integral, and derivative, together make the motor, pump, fan, and every machine controlled, stable, and reliable. In this episode, we will make these three concepts so simple that after hearing them once, you will never forget them in life. The simplest, most straightforward, and fundamental principle to understand PID is every industrial system has a set point. Sometimes we want the pressure to be 10 bar, sometimes the tank level to be 70%, sometimes the flow to be 200 cubic meters per hour. This is our target. Now, the actual reading of the system, which we call the process variable, is never perfect. Sometimes it is a little less, sometimes a little more, sometimes it remains stable, sometimes it gets disturbed. The difference between these two is called the error, and the entire philosophy of PID revolves around just one thing: to bring the error to zero. That's it. The role of proportional is to look at the error and respond immediately. Fast response, quick correction. The role of integral is to slowly eliminate small continuous errors, errors that are not visible. By integrating over time, continuously push the system gently until the process settles exactly at the target. The role of derivative is smoothing sudden changes. If any disturbance occurs, there is a quick jump in the pipeline, or the load changes suddenly, the derivative system calms down and prevents unnecessary rapid changes. If you understand these three roles, proportional fast correction, integral steady correction, and derivative smooth correction, then understanding PID becomes incredibly easy. This is the very foundation upon which the entire industrial tuning is built. Now let's talk about proportional gain. which is the heart of PID. The system's core reaction starts from here. Imagine your pump pressure should be at 10 bar, but currently it's only at 8 bar. That means there is a 2 bar error in the system. Proportional gain gives the system a signal that the larger the error, the stronger the correction needed. If the error is small, the correction remains gentle. If the error is large, it pushes the drive motor more to quickly bring the process close to the set point. P gain makes the system fast. The machine feels responsive. The operator thinks the process is reacting smartly. However, proportional gain is a double-sided tool. If P is too high, the system goes into continuous oscillation. The pump fluctuates slightly up and down, like 9.8, then 10.2, then 9.9. Such unstable behavior begins, which is risky for the plant. If P is too low, the system becomes lazy. Response becomes slow. It takes time to achieve the set point, and the plant feels sluggish. But when the proportional gain is properly tuned, the system starts running butter smooth. Speed remains clean, pressure stays stable, and the overall performance of the machine gives a professional grade feel. That's why proportional gain is like a surgical tool in the engineer's hand. The precision with which you tune P determines the stability of the entire process. Integral gain is the most misunderstood part of PID. People often think that integral is unnecessary or that the system will work fine without integral, but the truth is something else. Proportional action alone can never eliminate steady state error. You may reach the set point, but you won't be able to stay there. The system will drift up and down, just keep fluctuating. This is where integral shows its real magic. Integral collects the error over time and gradually provides correction. Just like a person solves a problem with patience, slow, steady, thoughtful. If the system is even slightly below the set point or slightly above, the integral notices that small error. It accumulates that error and gently pushes the system until the process settles exactly at the target. But integral also has a dark side. If the integral gain becomes too high, the system becomes heavily unstable. Overshoot occurs, hunting starts, surges happen in pressure lines, and the machine begins to behave jumpily. That is, the integral gain is both very useful and dangerous. Proper tuning is the real magic that unlocks this. When the I gain is balanced, the system's behavior becomes smooth, steady, and industry-grade stable. Derivative gain. PID is the shock absorber of the system. When the system receives any sudden disturbance, such as a valve in the pipeline opening suddenly or inflow into the tank increasing abruptly, the derivative reacts first. D-gain detects that sudden change and tells the system to stop and say, "Stop, do not react so quickly, understand the situation first." In other words, the derivative provides smoothness to the system, calms down its impulsive response, and keeps sudden jumps under control. But D has a major limitation. The derivative process amplifies noise. If there is sensor noise, pipeline vibration, or the signal is not clean, then D amplifies these small movements. The system can become unnecessarily jumpy. That is why in industry, the use of the derivative is very limited. Almost zero in pumps, almost zero in fans, and completely zero in level control. In these processes, D creates more problems and provides fewer benefits. But where precision matters, such as high accuracy speed control, position control, robotics, pick-and-place systems, CNC machines, there, the derivative is very valuable. There, D acts like a strong stabilizer, polishes sharp responses, and makes motion ultra-smooth. Understanding the derivative is an important milestone in PID tuning. Where to use it, where to avoid it. This difference creates a gap between a normal tuning engineer and a control systems expert. The control structure inside VSD is completely layered. This design is not the result of an accident, but the outcome of decades of research and industrial experience. At the very inside is the torque loop. This is the fastest loop of the system. The torque loop reacts in microseconds. It instantly adjusts the motor's current and ensures that the motor receives the required torque without any delay. Such a level of control is so fast that the human eye can never notice. Above this torque loop is the speed loop. The speed loop is relatively slow, but it is the actual decision maker of the system. It decides how fast the motor should run, how much torque to demand when the load increases, and how much smooth acceleration to give to the machine. The PID controller mostly works in the speed loop. It creates a balance between speed and torque so that the machine is neither jumpy nor feels sluggish. The real beauty of this layered design is that the system is both highly responsive and highly stable. The torque loop provides instant reaction. The speed loop offers smooth correction, and together they give the machine a professional industrial grade behavior. If you understand this concept, the torque loop is inside, the speed loop is outside, then you have understood the true core of industrial motor control. This is the foundation upon which all modern drives are based. Imagine you are driving a car, but there is no dashboard. You don't know the speed, you have no idea of acceleration, and you are just driving by feel. This is open loop control. The system is running, but without any real feedback. Now imagine you have a complete dashboard. There is a speedometer, an odometer, and cruise control is also active. You can maintain the car's speed exactly. If the road slope changes, if the load changes, the car still continues to run smoothly because the system knows in real time what the speed is and how much correction to give. This is closed loop PID with encoder. The encoder continuously provides feedback to the drive. What is the real speed of the motor? Is the motor slowing down or speeding up? Is the load increasing or decreasing? All this information is shared by the encoder in real time. Because of this feedback, the closed loop system remains stable, reacts quickly, and keeps these changes under perfect control. The machine's behavior with closed loop PID becomes industry grade reliable. No hunting, no random speed jumps, no unnecessary vibrations. Just smooth, controlled, and highly precise performance. This is the difference that makes a normal drive a professional engineering system. Today, I am sharing with you a harsh truth of the industry. In the real world, approximately 85% of plants are not properly tuned with PID. Sometimes the proportional is too high, sometimes the integral is so slow that the response is delayed. Sometimes the derivative seems completely unnecessary, and sometimes the time constants are chosen completely incorrectly. What is the result of this? The pump surges, pressure hunts, the level becomes unstable. The motor repeatedly goes into overload, noise increases, and the system starts tripping. The worst part is that people blame the drive, or the motor, or the process, whereas the real problem is only and only PID tuning. Today, we will see step by step how to tune correctly and how to convert the plant from unstable to smooth, stable, and professional behavior. Tuning is the cleanest, most scientific, and most reliable method, which is the step response. In this approach, there is no guesswork, no trial and error, only controlled observations. The process is simple. First, the integral is set to 0. The derivative is set to 0, and only proportional action is active. Then, the proportional gain is gradually increased. The machine's response is observed. As long as the system remains stable, P is increased little by little. And as soon as oscillation begins in the system, as soon as the speed or pressure starts to jump back and forth, Understand that the proportional gain has reached its limit. This is where the work begins. The oscillation started at a certain value, and half or slightly more than that, approximately 50 to 55%, is the safe proportional gain. After this, the integral is gradually introduced, just enough to make the steady state error zero. The system should settle cleanly at its set point. Never set the integral too fast, otherwise the system will become jumpy. And if still overshoot is observed or the system does not back settle after the peak, then the derivative is used a little. Only then, when it is actually necessary. More derivative always creates noise. Step response tuning is a universal method. Every OEM, every drive manufacturer uses this approach in internal testing. Whether mentioned in manuals or not, factory tuning is always based on this science. This is a technique that gives the engineer complete command over control loops. The behavior of pumps is naturally soft. Flow and pressure change gradually, so pump systems do not tolerate aggressive tuning at all. If proportional action is kept high, pressure hunting starts, sometimes up, sometimes down, and the pipeline becomes completely restless. If integral action is kept fast, dangerous surges are created in the pipeline, pressure suddenly jumps, and the system starts feeling out of control. Therefore, the most practical tuning for pumps is always balanced. Medium proportional action, slow integral buildup, and zero derivative. This combination gives pumps a smooth, silent, and stable behavior. The behavior of fans is completely different. Fans are fast response machines. Airflow changes instantly, and pressure also adjusts quickly. Therefore, in fan systems, integral action needs to be kept a little fast so that speed settles quickly and airflow remains stable. But one thing is common. Whether it's a pump or a fan, derivative action is almost never used in both. Derivative provides fast feedback, which in hydraulic and airflow systems creates unnecessary noise and jump. In practical field tuning, avoiding derivatives for both pumps and fans is the safest and most stable approach. Level control is my favorite topic because this process is the most delicate, the slowest, and demands the most patient behavior. The tank's level does not respond instantly. You give a signal, slow down the pump, adjust the valve. Yet it still takes time for the tank to react. That is why level loops never prefer aggressive tuning. The biggest mistake is adding derivative action. Derivative responds quickly, but the tank reacts slowly. Their speeds become mismatched. The result is that the tank continuously becomes unstable. The level never settles, and the system starts feeling even more jumpy. That's why the golden rule of level control is always simple. Low proportional action, medium integral action, and zero derivative. This combination provides the smoothest, most predictable, and safest results for tank systems. Level control is not only a science but also a test of patience. Whoever understands this, he begins to view process control from a new and professional perspective. Hunting is the most common issue in pressure control. This problem is visible everywhere in the field, and operators often think that the system is unstable. The reality is that the tuning is not balanced. When the proportional action is high and the integral action is slow, the pressure loop starts to overreact. Pressure systems are very sensitive. Even a small change can create a large effect in the pipeline. Due to this sensitivity, the system begins to hunt, sometimes up, sometimes down, and the pressure does not settle at one point. The most practical solution is always conservative tuning. Pressure loops do not favor aggressive tuning. A medium proportional response, medium to slow integral buildup, and, if the pipeline is very long, light derivative support. This combination provides the most stable results in the real world. By tuning this way, the pressure settles smoothly. motor does not give unnecessary torque jumps, and the machine exhibits a completely controlled, predictable, and stable behavior. This is the tuning philosophy that gives an engineer real confidence in control loops. The motor does not give unnecessary torque jumps, and the machine exhibits a completely controlled, predictable, and stable behavior. This is the tuning philosophy that gives an engineer real confidence in control loops. Integral windup is a silent killer. This problem is very common in the field, but engineers do not understand initially where the issue is coming from. Imagine your pump is running at minimum speed, the valve is closed, and the pressure has not yet reached the set point. In this situation, the integral error gradually accumulates. It keeps accumulating, and an invisible pressure builds up inside the system. Then, as soon as the valve opens, the drive reacts suddenly. Motor torque suddenly becomes high, the pressure spikes inside the pipeline, and the entire system feels unstable. The operator only sees that the machine is jumping, but the real root cause is the integral error windup. This is called integral windup, a slow buildup, which later explodes in the form of a sudden overshoot. Modern VSDs have anti-windup logic, which protects the system, limits the error when the valve closes, and keeps the process in balance. But this protection works only when the settings are kept perfectly correct and tuning is done thoughtfully. Understanding this concept elevates an engineer's control system knowledge to a higher level. Incorrect PID tuning is not a small issue. In the field, we have repeatedly observed that when tuning is not correct, pumps start surging, pipelines vibrate, motors begin to heat up, noise is generated, cavitation starts, and the levels in tanks overflow. Compressors also begin to run in unstable mode, and the entire machine behavior becomes unpredictable. All these problems are caused by the same reason: incorrect PID tuning. When an engineer properly tunes the PID, the plant's behavior literally transforms. Machines run smoothly, speed remains stable, and the process feels completely controlled. This is the skill that turns an ordinary engineer into a high-value professional engineer. In vector control, the motor's torque and flux are handled separately. This means that the drive has full authority over the motor. The drive decides in real time how much torque to deliver and how much magnetic strength to maintain. When torque and flux become independent, the motor's speed control becomes very powerful. If the load suddenly increases, such as a conveyor belt jamming, a pressure spike in the pump, or increased demand on a crane, the vector control immediately understands how much torque needs to be applied to the motor. At this stage, the true value of the PID controller comes into play. The PID speed loop makes the motor speed feel completely linear. There is no jerk, oscillation, hunting, or sudden overshoot. The drive continuously tries to keep the speed constant in real time, regardless of how much the load changes. When vector control and properly tuned PID work together, the system operates in a high precision mode. Speed response becomes the fastest, torque delivery stabilizes, and the overall behavior of the machine becomes professional industrial grade. The operator gets a feeling as if the machine is working thoughtfully. Smooth start, smooth stop, perfect speed control, and completely stable performance despite load disturbances. Friends, this was part 7 of the VSD series. Today we understood the PID loop not just as a theory but as a real engineering tool. Such deep and practical explanations are rarely found on YouTube because the purpose of ElectriVerse is to give every engineer the clarity that takes their career to the next level. From today's part, you saw that tuning is not just a game of numbers, it is a process of understanding the machine's personality. When PID and vector control are properly tuned, the machine runs so smoothly so stably as if an experienced operator is controlling it himself. And in the next episode, we will make a historic comparison. A comparison that industrial engineers always debate: soft starter or VSD. Which one is better? Under what conditions is a soft starter the best choice? And when does VSD become absolutely mandatory? In Part 8, you will get that clarity. The design, operation, and maintenance that truly provide value. If you found today's part valuable, then like, comment on which topic you'd like to see in the next video, and subscribe to the channel so that our engineering journey reaches you without interruption. Because creating a video requires a lot of effort, from scripting based on my experience to creating images on screen that are easy to understand. You were watching ElectriVerse, where every spark tells a story. Stay charged, stay safe, stay happy.